So we are reviewing the theory of finite dimensional vector spaces a little bit. We want to talk about basis and dimension. Let me remind you the setup. F is a field. V is a vector space over the field F, meaning there is an operation called vector addition from V cross V to V, and there is an operation from F cross V to V called scalar multiplication. If you give me a field element, an element from F and an element from V, I can get a vector in V again by multiplying alpha and V, called scalar multiplication. And they satisfy the usual axioms. We say that V is finite dimensional if there is a finite subset S in V such that the span of S is V. What that means is that every element of V can be written as a linear combination of elements of S. So if you give me a V in V, some V in V, then I should be able to find S1, S2, Sk from S, and alpha 1, alpha 2, alpha k from the field such that this combination is equal to V. In that case, we say that V is finite dimensional. So every vector can be written as a combination of elements of S with some scalar coefficients. Elements of the field in this context are called the scalars. Okay. Also recall, a subset B of V is called a basis of V. That's the key concept. If B is linearly independent and B spans the vector space. Meaning every element of V can be written in terms of as a linear combination of the elements of B, and B is linearly independent. It means that the only way a combination of elements of B is 0 is if all the coefficients are 0. So if B is B1, B2, Bn, then linearly independent means that whenever a combination like this is 0 for some scalars, then all the alphas must be 0. That's what linearly independent meant. Yeah. And we proved last time that finite dimensional vector spaces have a basis. Corollary last time a finite dimensional vector space has a basis. In fact, any vector space has a basis. In fact, any vector space has a basis if you assume what is called the axiom of choice, which is a basic axiom in mathematics which we usually assume. If you assume axiom of choice, or what is usually called in this context the Zorn's lemma. But we won't need this because we won't be dealing with infinite dimensional vector spaces much. By the way, and this finite dimensionality, so if you take Fn, like things like Rn or n by n matrices with coefficients in a field, these are finite dimensional. Whereas if you take the polynomial ring in one variable or a polynomial ring in two variables, these are infinite dimensional. Or in the real case, maybe you take continuous functions on 0, 1. These are infinite dimensional. In fact, we'll see that even, I want to add another example here because these are the ones we'll study. These are finite dimensional. this f is non-zero, irreducible. It doesn't even have to be irreducible, non-constant, yeah, non-zero is good enough. These are some finite dimensional f vector spaces, these are some infinite dimensional vector spaces. We'll be mostly concerned with these. Okay. And if you want to have some example of this spanning business, I wrote down a few vectors up here on the right, so 4 vectors in R3. So the first 3, for example, does not span R3. This is not R3. Because you can see clearly whatever linear combination I take of v1, v2, v3, the last coordinate is always going to be 0. If you multiply v1 by a number, v2 by a number, and v3 by a number and add, the last coordinate is going to remain 0. So you can never write, for example, this vector as a combination of v1, v2, v3. So these don't span. But if I take all 4, if I throw in 0, 0, 1, then you can check that every vector can be written in terms of this. So this is indeed R3. These 4 vectors, this set is not linearly independent. You can check that you can write one of them in terms of the other 3, or you can find some combination of the 4 that is 0, some non-trivial combination of the 4. For example, if I add the first and the third, then I get 2, 0, 0, which is also v2, so this is 0. So this is 1 times v1 plus minus 1 times v2 plus 1 times v3 plus 0 times v4 is 0. Here is a non-trivial dependence relation between v1, v2, v3, v4, so they are not independent. Whereas if you just take v1, v2, v4, you can check that these are independent, are linearly independent. In fact, these form a basis. You can check. Also spans, so this is a basis. What that amounts to saying is that every vector in R3 can be uniquely written as a linear combination of v1, v2, v4. Okay. So what I want to get to is that this fact, now that I know that every finite dimensional vector space has a basis, we want to show that any 2 bases has the same number of elements, and the number of elements in any basis is called the dimension of a vector space. So it's a basic invariant of the vector space, sort of a measure of the size of the vector space. We say it measures the number of degree of freedom in this vector space, number of independent directions, so to say, at least in the real case. So that's the theorem we are going towards. Want theorem. Assume V is finite dimensional. F vector space. Then there exists a number n such that any basis, so n non-negative integer, of V has n elements. We say that n equal to dimension of V. And we write is the dimension of V. And we write n equals dimension of V. This has a little problem with this. I mean, what do we do for the zero vector space? Maybe it's simplest to address that by declaring explicitly. Let's write this for non-zero vector spaces. Then this number is going to be at least 1, so a natural number. And then finally I'll say we define dimension of the zero vector space to be 0. Okay. And that solves the issue. To do this, we need to compare two different bases. So if you give me two bases, I need to know that they have the same number of elements. And the key is this lemma, which I'll write down now, and then we'll prove next time. The key to proving this theorem, the main work. So suppose B is a finite basis of V. And suppose B is an element and let's also give ourselves a vector and let V be a vector. Assume that, so if you give me a vector, I can write it as a combination of elements of B. Right, so something times B1 plus something times B2, etc. So suppose I have an element of B which actually appears in this combination. So this coefficient is non-zero. Suppose B in B, this is B, such that when you write V as a linear combination of elements of capital B, this little b appears with non-zero coefficient. The coefficient of little b is non-zero. So again, capital B is a basis, so if you give me a vector, I can write it as something times an element of B plus something times another element of B plus etc. A finite expression like this. Let's say B is a guy which actually appears, meaning appears with non-zero coefficient. That's the assumption. Then you can take this basis, throw away this B, and instead add this vector V. And this would again be a basis. This would let us compare two bases. So when you write V, this term actually appears. Then you can throw this away and instead add this in, and you'll still get a basis. This lemma would be the main technical work. Once you have this, it would allow you to compare two bases and prove this theorem. So we'll start with this lemma next time.